Hi everyone and welcome to AXA Arctic Live. It's really lovely to have you all with us and welcome to all those students and classes watching. I know that we've got schools from the UK, USA, Canada and France with us for this live lesson on the changing Arctic Ocean. Very shortly we'll be connecting to Dr. Helen Finley from the Plymouth Marine Laboratory, and we'll have her guide us through the changes that are occurring in the Arctic Ocean and a few special bits of science knowledge. Before we do that, I have a few shout outs to give to those classes watching. We have hello to Key Stage 2 at Cleveland's Prep School in Bolton. So hi to all the students there. A shout out to Carl Primary School in Derby. Hi to everyone in Derby. We have Elsa, Louis and Lola, and they are homeschooling in Suffolk. Big hello to you guys. We have Pembroke Elementary School in Virginia Beach in the USA. Hi to everybody watching from Virginia Beach. And a big Arctic welcome to Mr. Preston's class in Ely. Thank you so much for joining us. Just to go over a couple of bits of admin before we start, you will have probably seen the Q&A box to the side of the screen. Do type questions in there and we'll get to those towards the end of the live lesson. If there are any points that you need sort of clarifying or we're going a little bit too fast or there's something you don't understand, we'll try and cover those points off during the live lesson. So do just pop questions in as and when if they're sort of for clarification rather than more exploratory questions. If you want to have the video full screen, that's great. You can always access the app by going to the same page on a second device like a smartphone or a tablet. We will also have one poll which will appear in the same box during this live broadcast. Normally, AXA Arctic Live is broadcast from the UK's Arctic Research Station, and that is on the island of Svalbard, halfway between the north of Norway and the North Pole. We have a wonderful time working from there. It's an incredibly beautiful place, but with all the facilities needed to study the ocean, the glaciers, and the atmosphere from there. But sadly, like many of you watching, we have been restricted by the COVID pandemic and haven't been able to head north this year. But it's with great pleasure that I welcome one of our long-standing collaborators, Dr. Helen Finley. Hi, Helen, how are you?
Hey, Jamie. Hi, everyone. Nice to be here today. I'm doing very well, thanks.
Well, hopefully soon we'll be doing this back up in the cold. So it's a great shame, but thank you so much for being on this lesson about the changing Arctic Ocean with us. I think we're going to go through some basic science. So I think we've got a gas, a process, and a concept that we're going to share with the classes watching. Then we're going to do a couple of little investigation demonstrations. And then I think we've got a huge amount of questions, all about your experiences in the Arctic. So we'll share those with the students. I think we've got a few photographs and maybe some video as well, which we can share to give a flavour of what working in the Arctic is like. Helen, we're talking about the changing Arctic Ocean, and we're talking about changes caused by a particular gas, carbon dioxide. Just maybe as a refresher, I was wondering whether you could share with those classes watching what carbon dioxide is.
Yeah, so carbon dioxide, as you say, it's a gas. So around us in the air is lots of gases. The air is mostly made up of oxygen, nitrogen with some oxygen, but also lots of little other gases as well. And carbon dioxide is one of those. So it's around in the nature anyway, it's around in the atmosphere. And we breathe it out. Every time we take a breath, we're releasing carbon dioxide, we're taking in oxygen. Plants, conversely, they take in the carbon dioxide and produce the oxygen. So we're kind of in this natural cycle with carbon dioxide. And carbon dioxide is a great thing for the planet as well, because it's actually what we call a greenhouse gas. And you may have heard of things like climate change. And so greenhouse gas is actually take up some of the heat from the sun and keep it in our atmosphere, which allows us to keep the planet at a certain temperature. So it's a good gas. It's very useful, but it also comes with some problems as well.
And I think we're going to come on to, I mean, I think one of the problems that some students may have heard about is that it's contributing, you make this really great analogy that the greenhouse gas keeps the Earth habitable, has kept the Earth habitable, especially for humans over the past thousands of years. But with too much, we get too much warming. But you're going to touch on something slightly different. I think something called ocean acidification, I believe.
That's right, yeah. So as well as being a greenhouse gas and keeping our planet nicely regulated, like you say, if we put too much of that gas in the atmosphere, that's when it becomes a problem. And that's when it causes what we term climate change. So the changes in the systems that we're seeing, changes in weather patterns, things like that. But the carbon dioxide can actually get taken up by other things as well. So we hear a lot about how rainforests take up carbon dioxide, and they're called sinks. But the ocean is also a sink for carbon dioxide. So the ocean is a really massive part of our planet, covers 70% of our planet, and it's taking up that carbon dioxide all the time. So it's also a really important place for that carbon dioxide to be stored. The problem again comes from what happens with carbon dioxide when it goes into that seawater. So what can happen, I think we can see on screen is a little image of what happens is the carbon dioxide goes into the ocean and it can react with water. And that water and the carbon dioxide together make what we call a weak acid called carbonic acid. And that's fine on long time scales. So over thousands of years in the time kind of geological time scales, that's absolutely fine. That's a natural thing to happen. The problem is that we are adding so much carbon dioxide to the atmosphere so quickly that's going into the oceans much more quickly than ever before. And that's causing the oceans to actually become more acidic. So that is what we call ocean acidification.
Thank you so much. And do we have an idea? You talked about the ocean being a carbon sink, so it's taking carbon dioxide out of the atmosphere. Do we have an idea about sort of percentages or levels, the amount of carbon dioxide that is being absorbed by the ocean?
Yeah, so about 30% of the carbon dioxide that's been emitted that goes into the atmosphere from any of the industry, so any of the human-related activities, so cars, industry, things like that, about 30% of that has gone into the ocean over the last 150 years.
That's amazing. So the ocean's doing us a favour in some ways, but it also seems to be changing as a result. And you talked about this process, acidification and acid and these words here. What do those relate to, and how can we measure those? So
we talk about acidification. Well, what does that really mean? Acidification is really just a measure of acidity. So acidity we measure on a pH scale, and acidity is the amount of hydrogen ions in a solution in water or seawater. And we actually, I think there's a graphic here about the pH scale where you can hopefully see it goes from 1 to 12. And just like on a temperature scale, we measure temperature mostly these days on Celsius, where 0 is the point where water would freeze. And anything above that is all positive, it's warm, and anything below that we kind of call negative temperatures, and that's frozen essentially if we're talking about water. So just like that temperature scale, we have a pH scale which measures acidity. It measures those hydrogen ion concentrations. And we use water again as the middle point for that. So water, pure water would have a pH of 7. Anything above that is what we call alkali, so there's less hydrogen ions there. It's that they're being taken away from the system. And anything more than that, so becoming more acidic, goes down on the pH scale, which is a little bit confusing, is when you start to see things like lemon juice or soft drinks and things that start to have lower pH levels but higher acidity. So it's quite a difficult concept because it's kind of reversed. So if we're talking about more acidic, we're actually talking about a lower number on the pH scale. And when we're talking about the oceans, we're talking about the oceans, actually, they are slightly alkali. So they're actually around about 8.1 or 8.2. I actually have my pH meter from the lab here. So it's in some seawater, and there's a few wires in the way, but hopefully you can see there it's my seawater there is around about 8.2 something, 8.24. So you can see that the seawater I got from our lab yesterday is slightly alkali compared to pure water. So, and what we're talking about in terms of ocean acidification, this process of adding carbon dioxide and that producing this weak acid, is actually going to result in us just moving further towards the pH 7, so moving down the acidification scale. That's why it's called acidification. So we may be talking about changing from 8.2 to 8.1, which actually doesn't sound a lot, but it's about a 30% increase in acidity, which is quite a significant amount.
Absolutely brilliant, Helen. And just to relate acidity to objects that young people may have come across in their everyday lives, I believe that in terms of foodstuffs, so things that you would eat anyway. So please don't sort of test this on all the things on the graphic, but things you'd normally eat. There are some things that you would eat which are naturally acidic, and you get that sensation on your tongue, that sort of sharp flavor from, and then there's some things which are a bit more alkali. Is that correct?
Yeah, that's right. So it affects the sort of the sourness, the flavor that you would eat, you would get of food. Yeah, completely. So if you think about eating a lemon, that's very acidic, and it's quite a sour sort of taste. Yeah.
Brilliant. Thanks so much for that. I think what we're going to do, because there's a lot of science packed into what you've been saying. So I think what we're going to do, first of all, is understand the process of how carbon dioxide can change the chemistry of water, the pH of water. And then in a bit, we'll look at how or why that matters to those creatures that call the ocean home. So first of all, I think we're going to do this. If you can follow along in the classroom, please do. For this activity, you will need a glass, you'll need a straw, preferably a reusable one. You'll need some water. Tap water is absolutely fine. And you'll need a way of measuring the pH so you can see what it is at the beginning of the investigation and what it is at the end. Helen and I will be trying this investigation at the same time. So if you don't have all the equipment you need, you can always use our results. But Helen, I think, you've got this amazing, very special looking pH meter, which is measuring these acidity levels. I've got a sort of smaller one, which you can get online for about 10 to 15 pounds, which can be quite useful for school science. But are there other sort of really sort of like DIY ways in which you can measure the pH of a substance?
Yeah, definitely. There's quite cheap litmus papers that you can get. So that's just a bit of paper that will change color as you dip it into something. You can also make your own at home. Recommend adult supervision because you need to get some red cabbage and cut that up, boil it, and then take the juice, and it produces a nice purple liquid like this when you put it in water. And actually, if you have a play around at home, that's the kind of color that water is. If you add vinegar, it goes to a nice sort of red color. And if you add sort of the alkalis, the bicarbonates and things, that's a kind of blue color. Hopefully you can see the difference there. But yeah, have a play around at home. I think actually blueberries also work if you crush blueberries, but I think you need a lot more of them and they're a bit nicer to eat. So yeah, try the cabbage.
If there's a way you need to get rid of the red cabbage at home because it's not your favorite vegetable, you can ask who's ever at home to help you make some pH indicator. Do that with as many windows and doors open as possible. It can get quite whiffy boiling up red cabbage in the kitchen for a long time. So Helen, I'm going to put some water into my mini ocean, and we can get a poll up and just try and predict what is going to happen to the water as we blow through it. Whether you think that the pH will stay the same, whether you think the pH will increase, or whether you think the pH will decrease. And there's a poll that will come up online, and then we'll compare what happened with what you thought would happen. Just a couple of points. Sorry not to point this out sooner, but don't fill your glass up too full, because you get quite a lot of bubbles when you blow into it, and you don't want to spill those anywhere. Don't share straws if you're doing this in a group. Make sure you all have your own straw. And don't keep on blowing to the point of passing out. Take a break if you need to. So just nice and sensible, nice gentle bubbling. So we're looking at the science here. Although I have said to Helen, shall we see if we have a competition to see who can change the pH the most? So Helen, we, like all good investigations, we need a baseline. We need to know what is happening in our environment before we start. How are you getting on? You've got...
So I've got 7.2 actually in this one.
Oh, so what have I got? I've got 7.08. Okay. Right, we've got Ellie, who's a live producer behind the scenes, who's going to give us a minute, I think. So count it down. If you're doing this in the classroom, you can start when we start.
Okay, are you ready? On your marks. 3, 2, 1, go. That's 20 seconds done, 40 seconds remain. Halfway, 30 seconds left. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. And stop. Well done.
Wow. Thank you, Helen.
That was more puff than I think I have. Okay, let's have a look. I have got 6.4, still going down a little bit.
How am I doing? I can't quite see.
6.13.
6.13.
Yeah.
So I've gone down from 7.2 to 6.4, let's say. So not quite a whole unit of pH, 0.8.
Yeah, I'm about sort of 0.8, 0.9. So fairly similar there. So when we're looking at our predictions, I mean, just thinking about that, let's just have a look to see what people have thought. A lot of people thought, predicted it's going to decrease the pH, and we've seen that there. Just doing a couple of experiments like that, could we draw any scientific conclusions about the effect of carbon dioxide on ocean pH?
Yeah, well, I think quite clearly that demonstrates that adding CO2 can reduce the pH. To be scientifically accurate, we would have to be able to repeat that over and over again. So Jamie and I have done it. If any of you lot all do it, if we get every child on here to do it and repeat that, then actually that would show a nice robust, what we call robust result, so that where everybody is finding out the same thing. And so we would be able to conclude that this really does actually result in a change in pH.
And how, just in terms of science practice, sorry to put you on the spot on this, but how would we make sure it wasn't something else in our breath? Or, are those the kind of questions that you think about? Could it be something else that is causing this change?
Yeah, so to be really rigorous scientifically, what we try and do is control for as much as possible. So you would try and have the same amount of water, for instance, in everybody's glass. You would try and have maybe the same person repeat it over and over again, so that you're controlling for different amounts of gas in each person. And that might result in some variability. If you did it across enough people, actually that's probably even better, because if you repeat it with one person a few times, but then repeat it over lots of people, you're kind of really showing that there's very minimal influence maybe from other gases or anything else. We can isolate carbon dioxide and just do it with carbon dioxide if we wanted to do it scientifically enough, so we can take the gas itself and force that. So if you've got a soda stream, for example, at home, that's got a carbon dioxide bottle, which will bubble into the water. That's pure carbon dioxide. You can do the same thing with a soda stream and measure the pH. And so it is definitely CO2 gas that way.
It's quite surprising for any of you who do try that. I think the pH of sort of sparkling water is about 5.5, is about 1.5 units lower than tap water. It is quite surprising when you see that. Helen, I've got essentially I've got a big bottle of vinegar here, which is really quite acidic. And I think when I went down to the seashore, I saw that there were a lot of shells and, shell-like animals. So I got a bit of chalk, because that's a substance that shells are made out of. I'm going to put the chalk in the glass here, and I'm going to pour some vinegar in. Is that a little bit what's happening in the ocean at the moment? Are we sort of pouring vinegar on chalky-based living things?
Yeah, so one of the issues with ocean acidification is that calcium carbonate, or chalk, as you called it, it's found in all sorts of animals that produce shells or skeletons. So things like corals, for example, pteropods, and I think we've got maybe a picture of a pteropod we can put up. This is a free swimming snail. So you've obviously got the snails you find on the seashore, but actually there's all sorts of snails and animals that live in the ocean itself as well, that can float around and have these calcium carbonate, these shells that are made of essentially what chalk is made of. And in the oceans, naturally, this chalk would actually act to kind of buffer changes in acidity. And by that, I mean soak up, a bit like a sponge, soaking up that acidity, soaking up those hydrogen ions that make something more acidic. So over really long time scales, over thousands and thousands of years, if you add carbon dioxide and make the oceans more acidic, these sort of shells would turn into rocks that you'd find like the White Cliffs of Dover in the UK, or a chalk cliffs, and they would through weathering, they would actually stop that acidification from happening. But because we're doing this so quickly by adding carbon dioxide from human processes, the chalk and things aren't able to naturally buffer that. And so animals that are now swimming in this ocean potentially can be affected and start dissolving away, start kind of being corroded by that. And I think we maybe have a picture of a pteropod that's been dissolved. So you can see here, this is a picture of some pteropods taken from the Canadian Arctic, actually. And so they're already experiencing some conditions where their shells will start to kind of get little pits in them and start to dissolve away. And your chalk in your glass represents that. So it represents that shell of an animal, and the vinegar represents the acidification process. Now, obviously, this is a much faster process, faster experiment than is what is naturally going on. Vinegar, as you say, is much more acidic, but the process behind it is the same thing, yeah.
So you might be doing this in the classroom, and I'm just going to sort of hold this up to the camera here. What might we be trying to observe on this, Helen? I can see lots of tiny bubbles, and if you're doing this in the class either with a shell or a bit of chalk, you might be seeing sort of bubbling as well.
Yeah, so chalk works really well because it's got lots of tiny little holes and gaps in, and the vinegar can kind of work its way in, and you see these bubbles appearing. And so what it's actually doing is shifting that chemistry. So you're taking the acid and you're dissolving the structure, the calcium carbonate, and actually those bubbles that you see are actually CO2 gas being released. So it kind of is a feedback, what we call a feedback loop as well. So this actually speeds up the process more than would do in nature. But you're looking for those kind of things. If you're using a shell that is maybe a bit smoother on the top, it might not bubble quite so much, but you still should be able to see that sort of dissolution happening, especially if you leave it a bit longer.
Yeah, I think sort of going to sort of fishmongers or fish restaurants and asking for oyster shells because they've got all those ridges in it can actually be really effective if you're looking to do this in the coming weeks. And, you know, obviously, you know, we've looked at the pteropod, fantastic, beautiful creature in the ocean, and its home basically being dissolved. Is that what's happening to all shelled creatures, that they're basically having their shells dissolved in the ocean?
So it really depends on the animal and plants that and how they regulate themselves. So just like we have to regulate our body temperature, we have to regulate also our internal pH as well in our blood. We have a certain level of pH that we have to maintain. And animals and plants in the ocean are the same as well. So animals in particular have to maintain their internal organs, their internal blood at a certain level as well. And so anything that has a shell is extra sensitive to acidification because of this action of dissolution, so they could dissolve. But actually what we're finding is that it all comes down to kind of the energy budget. So just like we have to eat to have energy to grow, to run around, to do everything that we want to normally do, if you are not given enough food, you're put under starvation conditions, then you don't grow as much, things like that happen. Or if you have other stresses on you, then that can affect how you grow and develop as well. So just like that, for animals in the ocean, if you put a stress on them, like acidification, and you don't give them any extra food, then they have to use energy that's coming in and use it to maintain their shells or to kind of allow themselves to fix the problems that are happening as a result. And so they maybe don't grow as well, they maybe don't grow as big, they maybe don't survive as well in the long term. So it all comes down to kind of energy budget. And what we're finding is that if you do give them more food, then they actually are able to overcome some of these issues as well. So that suggests that food is quite an important part in providing that energy to overcome some of these issues.
Helen, I know when we've been together in the Arctic, you're normally studying the tiny wee animals in the ocean, the sort of the pods, the sort of, you know, the pteropods, the amphipods, the copepods, all these small mollusks and crustacea. Is this just an issue for these tiny wee animals, or are some of the larger animals in the Arctic affected as well?
Yeah, so what we're finding is that it can affect things at all sorts of levels. So like I said, anything that has to maintain its internal pH has a potential to be affected by a change in the external pH. So even things like fish, especially what we call the early life stages, so things like the eggs or the larvae, just like if a caterpillar has a larval stage, is a larval stage for a butterfly, fish and many other sort of crabs, things like that we see in the ocean that we think of as the adult, actually have larval stages as well. And those are the ones that are potentially most susceptible because they're so closely linked and so closely tied to their environment around them. So all sorts of things could potentially be affected. We're seeing impacts on larval fish. We're seeing impacts on a lot of the shell fisheries, so oysters, clams, things like that. But even if you think beyond that, indirectly, something that relies on that as a food could be impacted. So if you think of the classic Arctic food web, you've got phytoplankton at the bottom. They're the tiny plants that photosynthesize in the ocean. they're eaten by zooplankton, so these things like these pteropods, these copepods, things like that. Those are eaten by clams, for example, and those clams can be eaten by walruses. But we know directly that clams are going to be affected by acidification. And that means that there may not be enough food for things like walruses. So even though walruses, which are able to they have their mammals, so they're able to maintain their body slightly differently to some of the other creatures in the sea, they could be indirectly affected by these processes.
Helen, thank you so much. We've got a massive stack of questions, and I know people have got tons of things they want to learn from you. So we'll try and get through as many as possible. So the first question, very interestingly, from Cleveland's Prep, is: does acidification affect the deeper parts of the ocean too?
So yes, it does. So one of the things about the oceans is that acidification, although the carbon dioxide goes in at the surface, the way the oceans work is they circulate things like carbon, oxygen, and the nutrients around the ocean, and they end up going down and being locked away into the deep ocean. And so actually the deep ocean is already a little bit more acidic than the surface ocean. And so animals that live at the bottom are exposed naturally to these slightly more acidic conditions. But what we're finding is that because we're adding more carbon dioxide at the surface, we're acidifying the surface, it's causing this acidification to almost rise upwards as well. So things like the deep sea corals that we know a lot about, that live at maybe 1,000 meters deep in some places, historically, they've never been exposed to these kind of acidic conditions, but now because of acidification, that is rising up from the bottom as well, and that's potentially going to cover these corals, deep sea corals, with acidified conditions.
Brilliant. Thank you, Helen. Helen, we've got a slightly sort of different question here. It's from Akal Primary School, and it's: do you have any interesting stories about your experiences? Have you had any interesting experiences on your trips up to the Arctic?
Good question. Every trip has its own experiences. I guess one of my favourite ones is when we went up into the Canadian Arctic. We were camping up there. The second time I went, I was fortunate enough to go with the setup crew. So you have 4 or 5 people go ahead of the scientists normally and set up the tents and things. And you take a polar bear dog with you, what we call a polar bear dog, so a husky that is trained to watch out for polar bears, and they only bark whenever they see a polar bear. They don't make a sound. So I went up with the setup team. There was just 4 of us on the ice setting up all the tents ready for the rest of the scientists. We didn't actually have the dog with us at this point because he was supposed to come up afterwards with the science crew. He wasn't quite ready. There was a few issues. But we were out. We have to flatten off the runway. We're living on the sea ice at this point, so you have to flatten off the runway with shovels. And all of a sudden in the distance, someone said, "Did we leave some black bin bags over there?" And we're like, "I'm sure we did, but I don't think we left an oil drum next to that." And there was we had big white oil drums. And it turned out the big white oil drum wasn't an oil drum, it was a polar bear, mother and cub. And so we kind of had to just watch them come slowly down our runway before we were able to eventually scare them away peacefully. Everything worked out well, but that was one of my favourite encounters in the Arctic.
That's absolutely wonderful, Helen. Thank you for sharing that. The next question, this is from Burlington Jr. Have you ever been diving in the Arctic Ocean? If so, what was it like?
I would absolutely love to. I have not officially dived in the Arctic Ocean, no, but I've seen some fantastic footage of it, and by all accounts, it's quite dark. But someone likened it to, if you stand upside down on the sea ice, it's like you could play ice hockey upside down underwater, because everything is kind of just like a mirror surface underneath. Quite often on the bottom of the ice, it's green because you've got sea ice algae growing there, so plants growing there. And then you have kind of a community of organisms that live off that ice algae. So yeah, something I'd really love to do, but haven't managed it yet.
Okay, so under ice scuba hockey. There we go. That's for next year, maybe.
Yeah.
The question here is, how clean is the water in the Arctic? And that's from Elsa and Louis.
Thanks, guys. It's pretty clear. Pretty clean up in the Arctic. It's probably still one of the cleanest oceans we have. But it's probably like at least like a good swimming beach in the UK. But the more people are starting to go up into the Arctic, and it's being influenced more and more by industry, we just have to keep that in check. But yeah, at the moment it's doing pretty well.
Thank you very much. From sort of Eli St. John's, asking what qualifications do you need to work in the Arctic?
It really depends on what you want to do in the Arctic. You could have very little qualifications and go up as either field assistants or like come up and do some filming and things like that. You can do all sorts of things. We need all sorts of people to help out, not only scientists on the bases. We have project managers that set everything up. We've got base managers who look after us, look after the station, things like that. Field guides who are very good at kind of glacial work, boat work, things like that, technicians, engineers, electricians, and then of course the scientists themselves. And the scientists vary again from undergraduate levels, so you could just be going up as an assistant right through to highly experienced professors and things like that. So there's always a way if you have a will.
Brilliant. And just that term field assistant you use, those are the people who essentially keep scientists safe when they're at sea or on the ice or on the glacier.
Yeah, so they can be those type of people, and they can also just help with the science as well itself. So they could be scientific field assistants too. So they could be learning about the science as they go. Yeah.
Brilliant. Thank you very much. This is from Akal Primary, which is asking, what is your daily routine? And I'm assuming in the Arctic. Yeah.
Yeah, you probably don't want to know my daily routine at the moment. It's not very exciting. But yeah, in the Arctic, I guess it depends where we are, but mostly I guess we get up, we have breakfast, usual sort of thing. If you're feeling warm, then you could maybe have a hair wash. I think we have a picture of a hair wash that I once did at -40 in the Canadian high Arctic. So I wouldn't recommend doing it too frequently. We don't do that every day, certainly. It does make your hair kind of stand up on end after a while. And then we would go about setting up our science. So we normally have maybe a different job each day to do. So if we're ice coring, which is where you collect a sample of the sea ice, then we would go out and find the spots that we want to do that and spend the day collecting those cores, cutting them up, putting them back into our labs, ready for when we analyze them. Or if we're doing seawater work, then you either go out on a boat, or if you're on the ice again, you would maybe have a hole in the ice which you can put your instruments into and then collect seawater from. Once you have that sort of data, those sort of samples, then they either get shipped back to our labs at home, or we can do some analysis when we're out there. But quite often, there's not all the facilities that we need to do. So once we're finished, we'd have dinner. We're just like normal. Quite often, we'd then have a sort of nice, relaxed evening with our fellow field mates, and then off back to bed.
And just over to you slept in a tent?
Yeah, so we have done in the Canadian high Arctic, we had field tents. So very much like your kind of standard tent that you would go camping in. We have those. And then, like Jamie said at the beginning, in the UK, we have an Arctic research station, which is a bit nicer. It's a bit more like a kind of log cabin style of place where you can, it's got nice beds and things like that, showers and things.
Beds and showers, important things. And tea. So a few questions are really around the sort of acidification issue. How bad will it get in the Arctic? Will it affect humans? And can we do anything about it?
Okay, so will it affect humans? Not directly, I'll start with that one. Indirectly, maybe it could well affect the fish that we want to eat. It could affect the shellfish, things like that we want to eat. And in general, we rely on the oceans a lot for what they do to us, the sort of unseen things that they do for us. They help us regulate the climate. They help us provide habitat for things that we want. They provide that space that we want to go. Even just going to the beaches is a fantastic resource that those oceans provide. And if we change the oceans in this negative way, then it will impact on us as a society. In the Arctic, it's probably one of the most impacted places on our planet. Things are happening most rapidly there in terms of both warming and acidification. And that's because of the complex things like fresh water, the loss of sea ice, things like that, the opening up of the ocean without that sea ice on it. How bad will it get? Well, again, we're talking about relatively small changes in terms of the pH scale. So the worst case predictions, if we do nothing about reducing our emissions, if we do nothing about taking that carbon dioxide out of the atmosphere, then we're going to see the oceans get to around about maybe 7.4, 7.5 on average.
And that's by the end of the century, or
that would be kind of that's sort of 300 years time scale. By the end of this century, maybe around about 7.7, 7.6, depending on where we are. But that's enough. That's almost 150% more acidic than we've seen for geological timescales. So that's really a significant amount of change for the animals and plants that live in the sea. The problem is that the oceans work on very long time scales. So if you acidify now, and we have to act now to make a significant change, because otherwise this is just going to be ongoing for hundreds of years. It will take hundreds to tens of hundreds of years to get back to the pH levels that we have been at before.
And Helen, when you say sort of fastest in terms of geological timescales, we're talking dinosaur, pre-dinosaur?
Yeah, so at about the last 55, 65 million years was the last, it was called the Paleo-Eocene thermal maximum, which is around about the same time that dinosaurs were wiped out. There was a big CO2 event that was on the order of magnitude, so the same sort of scale that we're seeing now, but it happened, what we're doing is 10 times faster than that event. And if you think that event caused a mass extinction, then that's quite worrying for the sort of things that we can do. But we know we can do something about this one. We know if we act now, then we don't have to have these impacts. We don't have to see these problems. So I think the key thing is to really try and reduce what we call reduce emissions. And that's easier said than done, sat here. But what we can do and what you can do as individuals, as young people, is use your voice, your skills, your abilities to go and talk to people about what you've learned and why it matters to you and your future. And that has a big impact on how we then talk to policymakers and talk to people that are running the factories and things like that. So you can play your part, as well as kind of the usual sort of reduce, reuse, recycle, which of course is important, but using your voice to communicate is as important as well.
Thank you so much, Helen. And those great questions were from Cleveland's Prep, Burlington Junior School, and Michael Faraday and Laura's class there. Very sadly, we've only got a couple of minutes left. Can I do a very quick fire round with you, Helen?
Yep.
What's the most exciting thing you've discovered? And that's from Akal Primary.
I've discovered that seals are really smelly when they pop up into your hole, and I think we have maybe a picture of one of those. And it took us a while to figure that one out, what animal it was that was causing that fishy smell. But yeah, I've discovered that.
Is there a lot of plastic in the Arctic Ocean? And that's from Elsa and Louis.
Yeah, there is a growing amount of plastic in the ocean. It's not as big a problem as some of the other oceans yet, but it's a growing amount. And the problem we're concerned about with the Arctic Ocean is it's almost like a closed off sea. There's only very small entry and exit points. So any plastic that goes into the Arctic kind of does get stuck there as well. So we need to keep an eye on that one, yeah.
Brilliant. From Michael Faraday, have you been to Antarctica? I
have been to the Antarctic, yeah. It's a very different place. but yeah, I have been twice.
And from Ely St John's would like to know, how do you keep in contact with your family?
I tend to use, well, it depends where exactly you go, but you can use the internet if it's set up in that sort of place. Otherwise, it's things like satellite communications, so using satellite phones and things like that. But to be honest, if you're limited to satellite phones, then it's quite limited communication. You're kind of talking via someone else normally, day to day, and then maybe have a weekly conversation with someone from home.
It's about sort of, what, 50 minutes, half an hour every week or so?
Yeah, something like that. Just keep things limited. It costs an awful lot of money, I think, to run these satellite connections. So,
brilliant. Helen, thank you so much for sharing your insights into science and how the Arctic Ocean is changing through the process of ocean acidification. Thank you also for sharing what it's like to be a scientist up in the Arctic and some of the experiences you've had up there. Thank you also to all those students and classes who've been watching. It's been fantastic to have you with us, and thank you for all your great questions. But for now, from Arctic Live, it's goodbye. Bye-bye.